All right, so let's go ahead and get started. So this is module X1, Introductory, Analysis, Design, and Justification. So a brand new module for spring 2020. You guys can all feel special. All right, so let's get started. So first thing up here is I have learning objectives. I'm not going to read through these. You guys can read through them on your own time if you want. These aren't even necessarily what we're going to be doing today. This is sort of the end goal. So actually what I have on my end is basically a list of what I consider to be kind of the essential skills, if you will, or the essential properties, right, of somebody who is a mature problem solver. What you're seeing up on the screen is kind of the distilled list. There are actually about 20 of them, 25 of them that I ended up writing. This is something I did last month. And what these are basically are kind of a way to define, what you should be able to do, right, in terms of solving problems. Now, we're not going to really go through these kind of one by one or anything like that. The idea is that these are kind of my guides for what I would like you guys to develop a little bit, right? So there's nothing here, right, about using lists or using arrays or any particular technical skills. These are just kind of general things, right? Types of problems you could solve, right? Maybe approaches to solving problems, right? The things about the problem solving process themselves, okay? So to me, right, this is I suppose I should say this is an early revision, right? This is what I view as basically being a key aspects of what it means to be a mature problem solver, right? So you can maybe take a look at those, think about those later on. If you're bored and you want to see my entire list, which actually breaks this down, so each of these are broken down to about 5 other skills, let me know and I'll post those for you guys. This is kind of our direction we're heading in. This is probably what you would be expected to do by the time you got through with 334. So most of you guys are going to do operating systems with me next semester.
I'm doing class.
And so, if so, right, we'll finally get to here, right? It takes a little while to get there. Sorry, did I cut someone off? I didn't. Hopefully I didn't cut anybody off there. All right, so yeah. So let's take a look. So the first thing I want to talk about, and this isn't necessarily algorithms topics per se, is types of problems, right? So typology of problems, which is probably, that might be a new word for people. I'm guessing it's probably new. What we want to talk about for a second is just the categorization and types of problems you can expect to see, just in general. So let's see. Now, in these slides, right, there's a bunch of places where there are question marks, right? So there are questions I have for you guys. I do hopefully, right, want to see you guys, speak up. I know it's a little bit different than being in class, right? It's not as easy, but we do want to mimic, the classroom experience because that's, how we learn. Do try to speak up, right, as you can. All right, so we're going to start here, right, with basically types of problems. So not really thinking about algorithms specifically, not really talking about data structure specifically, although we'll have some examples from there. Let's just talk about type of problems, right? We'll start there. This is basically going to be motivation for stuff we do later. So you guys are in school, right? You guys have done 2 years of your coursework, right? You've worked plenty of problems in many different classes, right? You guys probably have, right, 60 credits, right, at least, right? Some of you have more, some of you have less. Right, you've been through a lot of class, a lot of coursework. Okay, so here's a question for you guys, right? And hopefully I can get some feedback on this. How are real problems different than what we see in a class, right? So you can think, right? We do stuff, right? You get homework from me, but then also someday, right? You hope to graduate, right? Fingers crossed, you hope to graduate, and you're going to go into the real world, and you're going to see real world, air quotes around that. You guys can't see my hands. Real world problems. How are those maybe different than the things you see in school right now? What do you guys think? Any
There
thoughts?
are a lot, this is Devonye speaking. There are a lot more variables that you have to consider, along with the fact that there's more constraints such as time, how efficient things can run, and I guess who you work with.
Okay. So a lot more. Okay. So I'll repeat that. So yeah. So Don's talking about variables, right? Number of constraints. Okay. And I don't. Let's see. Maybe I can. It'll be hard for me to write on the screen, I think. Because PowerPoint. Yeah. Problem is PowerPoint and Zoom.
Problems tend to be messier.
Problems tend to be messier. Okay. What do you mean by
in the real world?
Yeah. What do you mean by messier?
More variables, more unaccounted for variables, more people that you have to work with to solve them. You have a lot of times you have people's lives or well-being riding on them.
So okay. So we kind of had 2 big additions there. One is basically that a lot of the real world problems are solved in the context of a team, right? You're not really working by yourself. You're doing stuff with other people. which is really, I would think of as a problem solving strategy, right? Is work with people that have a different mentality. The second thing is that you maybe have a larger impact, right, from the result of your problems. Okay, so clearly, right, there's kind of a difference, right, than what you will probably, get paid money to do rather than what you've been doing in school, right? So that's a little bit concerning, right? It's concerning from the standpoint of how easy is it for you to transfer, to generalize your knowledge from a class into a real world, right? So yeah, clearly there's a little bit of a jump there. We need to investigate it a bit. So let's take a look at some educational problems here. So these are very familiar. So I screenshotted a couple of our homework questions from this semester, right? So this, I think, is from module, this is module 2 and 3, I believe. No, 3 and 4. I have to remember my module numbering system. So these are a couple of questions. Right? These are our I would say, archetypal, right, educational problems. So up top, you have one from analysis of algorithms. The bottom one, you have one on a list, right? So there's a short answer and a programming here, okay? And these, right, hopefully are familiar because you guys, did them, right? One of them is figuring out the tilde approximation. The other one is implementing a DQ using a doubly linked structure. This is what you end up seeing right now. Okay, look at those for a second. We got some questions down there to ask you guys. So let's think first about that top example. So my question to you guys is, what do you know immediately about this question, right? Or even the bottom one, right? What do you know without doing any work? Is there anything? What thoughts kind of spring to mind when you start looking at these question prompts? For me, I think I look at this and it's like, well, I have a narrow scope. If you're looking at the homework for module 4, the analysis of algorithms homework, probably the answer to it is going to be in that module, right? You're not getting asked a list question in the analysis of algorithms problem. Already, you've been narrowed down, right? So one of the problems with educational like homework, right? Trying to train problem solving is that things usually have a very narrow scope, right? One thing is they have a narrow scope, and the second thing is that scope is kind of made clear to you, right? You know what type of problem this is, right? And you kind of know, where to find out more, right? If you don't know how to do the problem, you can go read the book for that module because, hey, the homework is on that module, right? It got to line up, right? So you already know that, right? So you already kind of know, approximately where you need to go in order to figure out how to do this thing, right? If you don't know it off the bat. Let's see. What else might we immediately know? I'll go ahead and talk about actually, I see Ethan raised his hand. Ethan, what you got for me?
Yeah, with both of them, based just like on the problem we know a lot about, and just reading through it gives us a majority of the way there in terms of like narrowing our focus. So since you already talked about the first one, I can talk about the second one.
Yeah, confidence.
The second one, even like without reading the paragraphs, you can just see the file names, dq.java, base dq.java, and then the different method names with last, name dq and q front. So like we know that we're going to be working with queues. There's a front and a back, so then that means it's going to be doubly linked, and then we're going to have to do some kind of like fleshing out of what we've been given.
Yeah, it's all there. So you know what domain you're working in, and the problem itself is pretty well specified, which is nice for learning, right? I mean, one thing is that for like question 3 there, I think most people got the right answer right on the homework, and it was really nice, right? As a student, right? It's nice when it's like this question is self-contained. I know exactly what I'm doing, right? I can get I'm confident in it, right? That's a great thing, right? But it's great for education, but the problem is it's still in the realm of education. Looking down at the other questions here, we have things like, for example, what steps are involved in solving it? For both of these, right, I think you can look at these and basically think to yourself, hey, I know, what to do, right? So I could go thumb to the slide that says how to do a tilde approximation, and it'll give me some rules. And if I follow those rules, I'll be able to get the answer to this question, right? For the second one, right, what are the steps in solving it? Well, I mean, you're given some files, you're given an interface. You know that you need to download those files, open them up, read them, and then one by one, look at each of those methods and fill out the code inside them. Again, there's not really an ambiguity about what you do next. Okay, so a little bit easy. So let's jump down to the third bullet point. I'll see if anybody has comments on this. If somebody gave you an answer to either of these, would you be able to check that it was correct? What do you guys think? If somebody just gave it to you. I think we got one person agreeing that you could verify it. Anybody want to explain it further? We'll jump back to Ethan.
Yeah, if you're looking for like specific like formatting stuff, then it might be difficult, like depending on how you
Yeah.
want to lay it out. But generally, you can run it and give like certain different test cases, like you give us at the end of our own projects to figure it out. It's
Right.
not too difficult to check.
Right. So you probably would have a shot at it, right? So for the top one, maybe you would just try it again yourself, right? And see if you get the same answer. For the bottom one, you could look at the requirements, right? Your requirements are already listed out, write some test cases, and then you'd be able to see that that answer is indeed correct, right? So you have basically the ability to verify, well, you have the chance, right, of being able to verify the answer to either of these questions here. Okay? So yeah, it's a little, I mean, it's nice, but I'm not sure if that's realistic. Ethan, you got something else for me? Your hand's
No, I
still
forgot
up.
to put my hand down. My bad.
Okay. All right. Let's move forward. So this is education. These are educational problems. Let's take a look at some. Let's take a look at a very familiar real world problem, at least familiar to me. Just meet the course outcomes. Teach it like CSE 310. So this is what I was told when I was asked to teach 222, right? This class here. So I didn't get a book. I didn't get a syllabus. I didn't get a specification for what to do. That was my problem. Okay, I was told there are these course outcomes. You can do what you want. Just teach it kind of like CSE 310. Okay. This is basically what I got in my first meeting with my boss when I first started working here. So this I would consider to be a real world problem. And that I think, well, I mean, I'm assuming it sounds intimidating to you guys. I mean, I don't know. So real world problem, right? I'll read from the slides here because it's compact. A real world problem is typically characterized by being open-ended and ill-defined. So we're gonna actually introduce a bunch of terminology in this section. Okay. So this is going to look a little bit different than what we have for our academic educational problems. I should really stick to the word educational there. It's not really appropriate to say academic. Academic problems are real world problems. It's just that they're more on the theory side rather than application side. So yeah, so this is the problem, right? The problem of what Ruben's asked to do when he comes in for his job for the first time. So we'll look at the sample at the questions again. What do we know from this? What are my starting points, right? So we said, for the other one, right, we knew like the module was on, and we had some good ideas, right, for the programming one, where to go. What do we know immediately for this real world problem here of ask Ruben to teach 222 for the first semester? Crickets, which was a little cricket icon here. Anybody got anything?
I'm trying to understand the question, to be honest.
Yeah. So out of the box, right, we had some kind of knowledge about, oh, it's in this module, therefore it's on analysis of algorithms, right? So we know that immediately, right? We know this question has to be answerable with analysis of algorithm stuff, right, for the top one. Whereas the bottom one, we know that it has to be answerable with the linked list stuff, right? And we know that there is going to be an interface somewhere that tells us basically what to do for each of these, right? That's what we start with. What do we have for this one?
No, I had one yesterday.
So I think we got one comment here. So let's see, Joseph says, we have a set of standards to meet and an example to follow, but that's about it, right? So yeah, any additions to that? So that's a good start there. Actually, maybe our end too, but let's see if anybody else has any ideas.
Very similar to like what,
so basically, right, we don't have a whole lot, right? We do have maybe some standards, right, that need to be met, right? That's kind of a common thing in education, but there's not a lot about how to get there. Notice that second bit doesn't tell us a whole lot because it says like 310. Well, the problem is a dozen people teach 310 and they all teach it differently. And also, what does the word like even mean? I don't know what that means. You don't get a whole lot to start with here, right? You kind of just get a list of, oh, they should know how to use linked lists. They should know how to use hash tables. They should know how to use trees. They should know how to use graphs. That's all you start with. So you don't really know a whole lot. So if you were to do this, right, if you were basically being asked, create SER222 from scratch, any ideas what your steps might be? Jacob, what you got?
I mean, I guess you would start by just making sure that you understand or come up with some sort of definition for sort of those requirements, and try to sort of come up with develop methods to actually go about solving those or meeting those requirements. So, meet the course requirements, figure out what those course requirements actually are. And then CSE 310 is like a template course. So you could probably start by using that syllabus as a guideline, and then start coming up with, like with your course, various modules to, segment those course outcomes and structure it.
Okay. So there's a couple things there. First of all, there's the idea of definitions, right? So what is it we're doing, right? So notice it's not really defined here. It just says the course outcomes. So somewhere, right, there's got to be a little bit more information I need to bring in that basically tells me teach X, Y, and Z, right? There should be a little bit like that, right? And then maybe what I want to do is basically go look at doing some outside research and bring in some initial data about 310, right? See what it is they already have there, right? Okay, I see a few more hands up. Let's go, Tom, what you got?
You could probably find other instructors who like teach 310, and you can, if you've taken it, you can like take out your notes for the class, and then try to base it off of that. Use those as resources.
Okay, so you can maybe try to basically find out what is the basic pathway by the 310 was run, and then build from there. Dan, what you got?
Yeah, I was kind of going on the same route. Like you have to figure out a definition. You have to, like a base case, for example. You have to figure out where your boundaries are, what you where you need to start, and what that needs to include, and then where you need to end, and then kind of fill in the gaps from there.
Okay. All right, some good ideas from you guys. One thing, and you guys can maybe think about this yourselves if I can get the point to work, is what do you do if you don't have that? That's the harder version of the problem there. Is what if you don't have that? So that at least gives you a little bit of guidance. Dan says cry. For maybe you might guys find it interesting. I basically did the first part here. I was like, okay, I could teach like 310, but I want to be better than 310. So I was like, let me just ignore the 310 stuff for a little bit and do my own thing. So I did that all from scratch. I didn't look at a 310 syllabus. I just did it off the top of my head. And that was a lot of work. But yeah. So overall, right, this is a lot different, right, than our educational problems. Last one before we move on. If someone handed you a solution, right? So a solution basically is a 2-2. Could you check if it was right? So if I basically gave you a zip file of all the assignments and slides and everything else, could you check that it was correct? Was it a right solution to the problem of creating a SER222? Could you check that? Jacob?
I guess it partially depends on what sort of definitions the people devising that solution were working off of. Because if you have a different understanding of what those requirements are, then their solution might look completely different to your solution, and that's not even taking into account different ways of, even if you have the same understanding of the solution, there could be different I guess interpretations, implementations of that. I guess in that case it'd still be a bit easier to see if it's correct, but for me, I think it's more of if the understanding of the requirements are different, then that's where it can get tricky.
Right. So there's two things to do there. One is basically to make sure you have this firm idea of requirements, and that may not have here, because the problem is the course outcomes are stated with text, so they're effectively qualitative. And the second thing is you need some sort of a metric, right? So how do you even measure these things, right? There are different measures, right? So is letter grade a good measure, right? So a good SER222, everybody gets an A, right? Is that a good measure? It's not. But there's basically you need to have more specificity on what you're doing, and then how do you know that you're doing what you're supposed to be doing, right? It takes a little bit more. It's not just let's run a bunch of test cases, right? It's going to be a lot more work than that, a lot more. All right. Moving forward. Let's see if I can find the right window. There's too many windows open. All right, so we're going to go through, we're going to talk about basically, like I said, types of problems here. So we've talked about real world, we're talking about education, talked about real world. Let's start using some terminology you guys might see. So if you start basically reading the literature about problem solving, you'll see all sorts of words. So the first thing I want to actually talk to you guys about is problem descriptions. So how are even problems written down? So there are kind of three rough categories of problem descriptions that you'll see. So structured, semi-structured, and unstructured. And I'm not sure if you guys will have seen this terminology before. Some people might have, other people won't have. So what is this? Basically, this is kind of a way of talking about how well written a problem is, right? So this is kind of where we start. So if I write a problem, right, it could be what we call well structured, meaning kind of all little parts are sort of well defined, right? So all the elements of your problem are well defined. So you have so let's say you have X, Y, and Z, right? And they're related. This is addition. This is equals, right? And I know that they have to be equal to 10 or something like that, right? That's a well-structured problem, right? You can think of that as being a math problem, right? The kind of the structure of the problem is immediately apparent. So not only does the problem have structure, right? Meaning there's rules about how it goes together, but also all those relationships are immediately visible, right? Versus you may have a semi-structured problem where there's a problem that's been written out, right? But maybe even though it makes sense, right? It's logical, it's kind of hidden from you a little bit, right? So it takes a little bit of work to uncover, right? There's structure behind the scenes, but that structure needs to be extracted. Okay? Then the worst type is basically the last one there, unstructured. Basically, you're saying is your problem, doesn't really have rhyme or reason to it, right? It's maybe just a bunch of stuff mashed together, right? It doesn't really make sense. Maybe there's not even a way to solve the problem, right? I don't know. There's just kind of data there, right? So data, not information, right? So there's kind of these three different types of problems you'll see. Let's see. We can see examples on the right-hand side. So this one over here, right? This is a structured problem. Let's see if I can write. What is a tilde approximation? So basically what we're saying here is, this problem basically gives you everything up front. You have an equation, you can follow some rules, you get the answer back out. It's very clear what's being asked. This is a structured problem. This is what I call, the next one here is what I call semi-structured. This problem, right, is again the same, it's the same problem. These are all the same, by the way. But in the middle one, basically you're given a snippet of code, right? Now code has some logic behind it. We know the different parts go together. But it's going to be a little bit more work. I have to basically write a growth function. I have to extract information in order to figure out how this thing goes together. Okay, so it's a little bit more complicated, right? So so there's structure, but it's hidden from us, right? The structure we're looking for is basically this expression here, and over here it's basically hidden inside of our code. Now the bottom one there is unstructured, and it basically just says how much time does it take for a program to print hello, hello versus hello, 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 hello versus hello a bunch of other times. That's kind of miserable, to be honest. I mean, I don't really know what you'd do with that. I mean, if you look at it, it does kind of match up, right? So if you look at the progression of the hellos, right, the numbers will roughly match up. It's not very useful, right? So yeah, so these are three types of basically problems you guys, or I should say problem styles you guys might see. Let's see. For those of you who know about the annotation tool in Zoom, let's try using it really quick. What is it? Which one of these is basically the type of problem that you typically see in homework? Can you guys basically just make like a mark on one of these, right? So you can make a mark over here, right? Let's just try out the annotation tool real quick. Can you guys mark for me which of these three is most likely to occur on a homework in the class you've seen? So in Zoom, right, there should be basically an annotate button, and it gives you things like the ability to draw, and then select your color, and you can even do little stamps and stuff like that. So I see somebody managed to do it, so I see a little bit of green there. Anybody else want to throw in a vote? Okay. Structured. A couple votes for structured. Vote for semi-structured. Okay. Yeah. And so, by the way, you guys should feel free to write on my screen. Just don't do anything too bad. But yeah, you can write on my screen. Okay, so it looks like most of the time people are putting structured, then some people are putting semi-structured. So yeah, that's typically how it looks, right? So as you guys start, right, in kind of lower division classes, almost everything is going to be structured, right? Or when you take classes like math classes, again, it's going to be structured. They'll tell you exactly what you need to do. Versus, right, as you go up, right, things get a little bit more, well, they're still nice problems, but they're not all given to you immediately, right? Things become semi-structured, right? So in this class, in SER222, basically most stuff is going to fall into this category here. Versus if you take, for example, SER222 with me, things are going to look like this. And as you go up, they'll kind of get more complicated and more complicated. Maybe as a kind of archetypal examples, you'd say that, you know, structured maybe is going to be, you know, Calc 1 is the most structured problems you'll see. Versus unstructured, well, anybody know what course number I'd put in there for a SER class that has unstructured problems? Anybody want to take a stab at that? Starts with a 4.
Is it like your capstone stuff?
Capstone stuff. So that'll be the closest you get to unstructured, because your sponsor will basically come to you and say, hey, build me an X. And that's all you get to work from. So yeah, there's kind of this progression, right, from when you start the program to when you get out, right? So like I said here, just think of it, right, is the math's going to be super structured, capstone is going to be unstructured, right? So we need to get from, and ideally, right, we want to progress from one to the other, right? We want to be able to do anything. All right, so questions there for you guys at the bottom. Which of these is easiest to solve? And the be careful remark is kind of important. Jacob, what you got for me?
I mean, I guess you would usually think possibly the structured problem would be the easiest to solve. However, I think it does also depend how you define the requirements for your unstructured problem.
Mm-hmm.
So if you're given, you know, if you're given some, you know, some question and there's some, you can sort of come up with your own ways of defining those requirements to, you know, solve the problem. So you could make those very simple requirements.
Right, right. So in a structured, right, typically I think the first instinct is like, oh, the structure is going to be easiest. And it is kind of true, right? They may be the easiest to make progress against. But in terms of overall, unstructured problems give you more flexibility, right? So there'll be unstructured problems you see that are terrible because they're not well defined and because they maybe even ask you to do something that's impossible. Well, on the other hand, they'll give you a lot of flexibility. So when your sponsor in capstone comes to you and asks for something, well, maybe it ends up being that there's a little app maker that does it for you, right? And the requirements aren't specific about, oh, you got to write this in C#. The sponsor doesn't care, right? All they have is this general idea of what they want to do. Well, then you actually are in a better position, right? So I would say that really, right, we want to think of it maybe in terms of a safety, right? So a structured problem is always going to be safe to work on because everything's laid out for you, versus unstructured. It's going to be a little bit of a gamble, but maybe it'll be easier. Or I guess maybe it could be harder. So yeah, I agree with everything that Jacob said there. All right. Let's see. I don't know. Let's see. I'm looking at my last question there. What is specific differences in information here? Actually, maybe I'll just talk through this one. Let me go back. Go forward. So just really briefly, I want to mention some things here. Okay. So this is actually over here, this little question. Basically, this is with regards to our examples on the right-hand side of the screen. So just really quickly, I want to point out that basically, right, so all these, right, are about information content, right? So information is, you know, hopefully is the foundation of knowledge, right? What do we know about our problem? Here, right, all the information has been distilled into this expression. Versus over here, our information about what work needs to happen is kind of spread out over this, right? This is basically a summary. I should get out my tablet. My tablet is on. Okay. Does that work? Let's wonder. Let me see. No, it doesn't. It does that doesn't want to work on my secondary monitor. All right. So I have some information content there, right? That's boiled down or summarized in that expression. Really, it comes from this code here, and then you know.
I love you.
And over here, let's see. Actually, I need my pointer back. Then we have, right, this stuff over here. This is again information content about my problem, but it's been kind of occluded a little bit, right? I see that there's, you know, these sequences of hellos being printed, but I don't really know, you know, what they mean or how they got there, right? So it's like I'm being hidden from view. It's like I'm trying to look at an object, right? But all I can see is its shadow. I can't see the object itself, right? So like so if you imagine, I guess, picture an object, right? So you have, you know, a book, right? On the bottom, it's like you look at the shadow, right? Kind of evidence that it is a thing, versus being able to look at the book itself, or being able to have someone specifically tell you, oh, this is the ISBN, this is the title, right? That would be another way you can think of, you know, structured, unstructured, semi-structured. So this, I would say, is maybe I would say hidden somehow. hidden, messy. Yeah, there you go. All right. So yeah. Questions, comments, concerns, complaints, critiques. Otherwise, we will move forward. All right, moving forward. So we have two kind of big aspects of problems we want to talk about, right? So we're gonna, this is right, it's those problems in general, right? Eventually, right, we'll come to algorithmic stuff, but it'll be a little bit. So the first kind of axis I usually think about in terms of real world problems is open-endedness, right? So closed-ended problems are things like, you know, a structured problem, right, or a math problem. Basically, it's a question that has one specific answer, right? And maybe the ways you get there is laid out in specific rules. You have to follow this set of rules. You have to do this, and then you'll get the answer, and at least you'll get the right answer every time. That's kind of a closed-ended thing, right? Same answer all the time, kind of the same ways to get there even. Versus an open-ended problem. Open-ended problem, right? Basically, I'm kind of left open for what will the answer look like, right? There might be different answers that are valid for it, right? Really, there are some constraints on the answer, right? So the answer has to look like this rather than the answer has to be this thing here, right? So rather than the answer being x equal 5, any positive x could be the answer, right? That type of deal, right? So we have kind of this little dimension here. I will end up adding to it, right? So closed-ended versus open-ended. So let's see here. Let's see. So I have 3 examples here. Let's see. For my first example one, what do you guys think? Is it more likely to be closed or open? Right now, actually, let me put a little. Maybe I can put a little votey thing here. I'm going to clear my screen. I need to clear. Where are my clear options? I want to clear guys' annotations, and I'll ask you to please. No, I said clear. Annotate. I guess I'll use eraser. All right. Okay. So we'll draw this really quick here. So we have some examples here. I just want you guys to tell me, we'll do this kind of like voting here. Closed or open? What do you guys think for number 1? Put a little mark in these boxes, right? So you can do something like that on my screen. Closed or open-ended? Okay. People are thinking closed. I kind of agree with that, okay? Because the answer of that is basically just going to be like 5n squared, right? There's one specific answer. I can't really debate this, right? Is it that or is it this? It's going to all be that. It's always going to be the same thing, right? So that first example I would say is a closed problem. All right. Let's see. What about example 2? Write a program to take the sum of the first n positive integers. So it's stated there. Is this closed or is this open? Okay, so people are saying it's open-ended. So I see people saying it's open-ended. Okay, so it's open-ended. So let me ask you guys this. Does it matter that I'm being told very specifically what to do, right? So it's not ambiguous what I'm supposed to do. Does that matter? Ethan, what you got?
No, it's saying what our goal is, but we can do it however we want.
Right, it's saying what our goal is, not prescribing a specific solution, right? So I can do it iteratively, I can do it recursively, I can do it a million different ways, right? So this problem is well defined, but it's not. So it's well defined, right? But that doesn't mean that it's not open-ended. So yeah, it is. So that's correct too. Okay, so looks like people are good on that one too. All right, the last one. Consider designing a program where you need to store a fixed collection of items, which you use in an array or a linked list. Is this open or closed? Okay, a bunch of people are saying open-ended. What does the answer to this last question look like? The answer to this question over here, right, is probably going to be something like, yeah, because you guys are kind of wrong. So yeah, and then instantly it moves over. So one thing here, as we look at this, right, we want to know what does the answer look like. Well, notice here, right, we're saying would you use an array or a list, right? Our answer is only one of those 2 things, right? So our goal is very specific. So even though I know it sounds open-ended, really what it is it's a problem that's, I would say, maybe underspecified, right? So there's a little bit of ambiguity there. But in the end, right, it'll distill down to an array or a list, right? So I can make a list, right, of my possible answers here. For the second question, I don't know, right? I mean, how could I make a list of all the programs that can compute the sum of those numbers? That would be impossible. There's a million programs that could do that. Whereas here, our answers are just list one array. So it's a little bit simpler, right? So I know that was kind of tricky, right? That's a different kind of type of problem. All right. Questions, comments, concerns, complaints, critiques. Otherwise, we will move forward. All right, let me move forward. As soon as I can get context to the right window, I'll move forward. All right, so there's a lot of text on this slide, but I'll kind of just talk through it all. So when we talk about open-endedness, the reason why it's kind of familiar to us is because as engineers, people are typically, I want to say us, but I can't, right? I'm not an engineer. Engineers are typically asked, right, to solve what they call design problems, right? So a design problem is basically a problem that has the flavor of, well, it has kind of two flavors. The first is basically picking one option among many, right? So it's like, well, I want to design, a piece of software. I want to design, a fastener for a door, right? There are a bunch of different ways to solve each of those problems. We are asked to find one that is appropriate for us from the kind of the search space, right, or the solution space of all the possible ways to solve that problem, right? That's one sense in design. The other sense of design is it's not always clear what is the best answer, right? So it's hard for me to say this program is the best way to do something. I mean, we do have ways to do that, right? And we've seen that, like, for example, when we did the sorting algorithms, but it is kind of hard to do, right? How do I say this is the best? It's not always, immediately apparent. So these are kind of the essence, right, of a design problem, right? Is picking among alternatives, not really sure what the best it is, right? And this is kind of archetypal for what engineers are asked to do, right? Because engineers are handed problems like, build XYZ, where XYZ is just a component in a system, right? And it's like, well, I don't know exactly what the answer will look like. It'll take me a little bit of work. I have to design something, right? I have to kind of go to the void, right, and fetch an idea from that, right, that'll solve my problem, right? So design problems for us, right, are something simple like, writing a program. They can be all sorts of things, though. The example that came to me when I was writing this slide last night was a design problem, right, is something like converting an idea into a sentence, right? So I want to say something. I could map that into English a whole bunch of different other ways, or even to other languages a whole bunch of different ways, right? How do I know that one of those answers is good? I don't really know, right? Usually the open-endedness, right, that we see comes from the fact that things aren't kind of well-defined or are underspecified, right? So it's like, well, you guys, I'm not going to tell you, what programming language to do. Well, all of a sudden, I got to pick the best programming language. It's hard to pick the best programming language, although we all know Lisp is the best. It's hard to pick the right programming language. There's all sorts of kind of flexibility you have in your problem, right? How you approach it, what do you do, right? So in practice as engineers, right, what you guys expect to see is these problems, right, that are these open-ended things, right? It's not going to be find the tilde approximation. It's nothing like that. It's going to be something open-ended, like build me a piece of software, to monitor the supply at all the different Starbucks in Arizona, right? That type of thing. I don't know. Okay. Hopefully you guys have heard some discussion of design already. Have you guys, who has talked to you about design already in your classes? Who's talked to you about design? Anybody want to throw some course numbers in text chat or right on the screen? Where have you guys heard about design before? Okay, 216. I think most of you guys are probably taking 216 right now, right? Right now. Okay, and then Doug. Okay, so a couple classes. Yeah, I think, well, 240 right is already packed with a lot of stuff. Usually probably where they start getting, so Doug will probably do a little in 100. I think for 216, they jump right into what they call modeling, right? So representation of a system, saying that, okay, we need to summarize this somehow, and then we'll introduce UML as basically a way to talk about what we're doing, right? So yeah, so this is kind of the point where we start to talk about design, right? We're moving away, right, from those structured problems, these semi-structured or unstructured problems, right? That's the direction we're going in as you guys kind of move up. All right. One more slide here, and then I'll probably have you guys drawing on my my screen again. So another kind of axis, right? I feel bad about like I'm gonna get rid of all these hearts. I don't want to erase people's hard work. So another axis, right, we could talk about is the idea of how well defined a problem is, right? Well defined versus ill defined. So a well defined problem is one where basically everything is clear, right? I know what I start with. I know what my choices are. I know what my answer will be when I see it. Right? So for example, that tilde approximation, right? I know what I'm starting with. It's exactly that expression. I don't have to go look anything up. I don't need to search for anything. I don't need to do any experiments or research. My starting point is well-defined. I have it right there in front of me, okay? So that's a well-defined problem. Whereas an ill-defined problem, it's not really clear what I'm starting with. I don't really know what to do next, right? I don't even know what an answer or a solution might look like, right? So this is another axis in addition to being kind of well-defined, or in addition to being open-ended versus closed-ended, right? Is I can just basically have a question that's in a sense well-written versus poorly written, right? So and then up there, right, you see the kind of the primer up there as I have my little bar there for well-defined versus ill-defined, okay? So this is another axis. This is kind of related to other terms. I don't know if you guys have seen these terms before. So underspecified problems, ill-structured problems, wicked problems. I don't know if you guys have seen those before. Have you guys seen those words at the bottom before? I don't know. I'm not really sure who would have told you other than me. Those, if you want, you can go on Wikipedia. There's pages for each of those, and those are kind of different degrees of badness for a problem, if you would. With wicked problems being kind of the end one. A wicked problem is maybe analogous to an impossible problem, but the impossible there is somehow different than, for example, the impossible we talked about when we did analysis of algorithms earlier in the class. Okay, so we have this idea of open-ended versus closed-ended, well-defined versus ill-defined. Let's try practicing a little bit. So this next slide, which my Windows always lose contact. This next slide basically is going to be another thing where we can draw on it. So we got some examples here. All right, so you have a couple of axes here. Basically for, let me erase a few things here. So you have your axis, right, for closed-endedness, right, versus well-definedness, right? We have that there. Let's try plotting these. So I'm going to put some numbers on there. For the first one, finding the tilde approximation of a function, can you guys maybe draw me a little one where you believe it would go here, right? So how open-ended is it? How well-defined is it? Where would my number one go here? And so you should basically be like, imagine the screen, right? So, okay, somewhere over there. So I got some ones going over there. Okay, so it looks like we're in that quadrant there. So closed-ended, well-defined. All right. All right. So it looks like most people are going to axis. Anybody want to explain to me why that belongs over there? So it looks like that looks pretty good to me. Anybody want to explain why? What makes it both closed-ended and well-defined? Well, here, right, I can think of it as being well-defined just because I have, I have a formula, right? I know the definition of a tilde expression. Those things I all know. In terms of closed-endedness, it's pretty closed-ended as well because, hey, there's one exact answer to this thing, right? I don't have a bunch of different variety. So yeah, that position kind of makes sense to me. All right, what about for number two? Where does number two go? Okay, so I got some. We need the number two. I don't know what heart corresponds to. Unless somebody writes a heart, unless somebody defines for me what heart means, I don't know what number heart is. Yeah, it's best if you guys can draw the number. That way we know kind of which answer you're going for there. Okay, so we got some over there. Okay, so people are saying it's well-defined, closed-ended. Anybody want to explain why? Whoever, yeah, I was gonna say keep on adding those. Whoever's adding the little symbols there makes it easier. So yeah, so this next one, right? Basically, we're looking at it as in it's still closed-ended, right? Because no matter what, I should always get the same answer, right? The method is what it is, right? If I analyze it, I should get the same result every time, right? There shouldn't be any disagreement about it. It's still closed-ended, but it's a little bit more, ill-defined, right? It's not too bad because I have program code, but it is more, right? There's more in the way, right? There's more separating me from that growth function, right? Separated from the tilde, right? So it's a little bit more work for me to go and figure out what's going on. So yeah, I think that's a good position as well. All right. So hopefully somebody can speak up now because I want you guys to give me anybody can give me an example of a problem we could plot up here. You can just shout out one. Anybody have ideas? Raise your hand if you got one, or just talk on your mic. I want to do at least one of these that's of your guys' choice. What could we put up here? Ethan, what you got?
I was thinking of the delivery man problem that we went over.
Okay, so the traveling salesman problem, right? So it's like, well, I got a bunch of packages, right? So the poor, right, UPS and everybody's dying right now, but they gotta basically deliver packages to every single location in a neighborhood. How do they do that? Yeah, so we'll call that, and that's called we usually use an acronym TSP. Traveling salesman problem, yeah. TSP. Where might TSP go, right? So that's basically the problem of I want to visit a bunch of different locations in the least amount of time possible. Is it well defined? Is it open-ended? Is it closed-ended? What do you guys think? I guess we can put an arrow there if you guys, yeah. So we got the arrow. Okay, so it's more so more open-ended, yeah. So we're not being prescribed how to solve the problem. We can solve it any way we want, right? So we could brute force it. We could use, I don't know, genetic algorithm techniques. We use awesome machine learning stuff. We could do it a whole bunch of different ways. Okay, so it's definitely open-ended. In terms of well-defined, I would say it's probably more on the upper side there. There's a way for me mathematically to state that one route is faster than any other possible route. Right? You can imagine you do that like for each and for all thing, right? Those global quantifiers. So I think it'd be pretty well defined. Okay? So I would say probably goes a little bit on the, well, it's definitely open-ended. So with that axis we're good on. I think I would kind of lean a little bit more towards the well-definedness. It is kind of a classical math problem. All right. Any other examples for number 4 that people would like to do? Otherwise, we'll do number 5. If anybody can think about something, shout out the next couple seconds. Otherwise, I think I'll just skip down and do number 5. All right, let's go ahead and just do the number 5 one there. It's David. Okay, we'll do that. Okay, you know what? We'll do it. I honestly don't know how serious David was, but we'll do it. Will I get in trouble for this? I don't know. Okay. So number 4, the ideal form of government. Is that a well-defined versus open-end versus ill-defined closed? Where does that go? Put a check mark over there, or number 4. Yeah, terrible.
Where
right?
it goes is the realm of philosophy.
Yeah, it's both open-end and ill-defined, right? I mean, it's not really clear. Like, just the word ideal there is terrible, right? Yeah, that's not a good time, right? We don't have time to solve that problem in today's class. We'll do it some other time. All right. What about for the last one? Curing COVID-19. So the reason we're all stuck at home here and we haven't left we hopefully haven't left the house. Where does that go on this chart here? So number 5. Okay, so we got both sides, right? Okay. So let's see. Open-ended. Okay, so I think probably it's going to be open-ended, right? Because there's maybe a million different ways. I mean, we can create a vaccine. We can just quarantine everybody and lock down the whole world. I would say it's probably going to be on the open-ended side. And then in terms of well-definedness, I mean, to me, I would probably say it's more ill-defined than well-defined because I don't really know what a cure is. Does that mean that nobody gets sick, or does it mean the virus goes away, or like what exactly does it mean? So I would say it's definitely going to be super open-ended, and then either to the middle or to the bottom of the kind of the ill-defined axis. All right. Question here for you guys. Is it correct to view these as being orthogonal? Right. So I have basically these 2 axes set up. Is it correct to view them like this? Yay or nay?
Yay.
So, okay. Let's see. Maybe I'll try to draw a little poll here. I'll put my yes or no. You can put your notes, your marks under there. So yay is both ill-defined and open-ended. Okay. So most people say it is correct to view them as orthogonal. Okay. Yeah. I was actually vaguely hoping that someone would contradict me there because I couldn't think of a contradiction, but that's because I didn't think of one. So yeah, sometimes they're right. They're a little bit related because it's like, well, a problem that's bad is a problem that's bad. But it's possible, right, for a problem to be well-defined, but well, to be well defined but but open ended, right? Or ill defined but close. I can mix and match those, right? So they are different things, right? Sometimes people combine them. Really, they are different. All right. The person who put the O under the no, do you have anything to talk to me about? I'm interested in hearing counter examples, or maybe I don't know. People also are doing other things. So okay. So I think we're good here. Let's move along. So let me clear my screen. And we'll proceed. All right.
Hey, Mr. Kuna, I just have a question real quick.
Yeah, Vic, what you got?
So there's like a assignment for Module 8. Are we doing that right now?
I don't think I'm gonna do it right now. I don't really want to rush you guys.
Okay.
I'll just see. I might give it as a take home. I might give it as a take home, right? Meaning rather than not having a time bound on it, because I know you guys are available here, right? But I might end up just for today, like just letting you guys do it whenever, like today or tomorrow, if that works for you guys.
That's good.
Okay.
Cool.
Yeah. So
All right,
yeah, because I want to make sure I get through a certain number of slides here. All right. Yeah. So thanks, Vic, for reminding me about that. I meant to say something earlier, but yeah. Because I was gonna do it, but then I need to finish the things here. All right. Let's move forward. So other things to talk about, right? So let's see. So ill-definedness, right? So I want to talk a little bit more about ill-definedness for a minute, because that's something that basically we don't see a lot in the educational problems, right? Everything's kind of laid out for us, right? But a lot of times, right? So either things are laid out for us, or we don't see the ambiguities that are there. And we'll see some examples on the next slide. So a lot of times, right, you have question prompts basically that there is, I shouldn't say question prompts. You have problems that are given to you, right? Maybe you encounter them in your life, maybe you're given them by your boss, I don't know. But some part of them is kind of ambiguous and unclear, right? And we don't really know what we're supposed to be doing, right? So there can be a lot of basically problems with the question prompt, right? So, or the question, right? So some part is, underspecified or unknown, right? Simply, right, you're asked to do something where it's like, okay, I don't know. Let's say you're asked, let me see. Let's say, for example, I tell you that the exams are take home, but you need to leave your grade exam at my house. That problem is a bad problem because you don't know where my house is, so you don't really know how to solve it. You, in fact, don't really have any shot unless you can find somebody that knows where I live, right? That could be a problem. Not to mention if you're not even in Arizona right now. You can have problems, right, that are underspecified, right? So there's kind of a difference here, right? Sometimes you have a complete unknown, right? Versus something that's just like, I don't know enough. Like, Ruben lives in Arizona, so I know that you at least get to Arizona in order to give him your exam, right? So it's underspecified, right? So I need a little bit more information. And then sometimes, right, you basically have the case where something cannot be known, right? So when we talked about analysis diagrams, right, we kind of mentioned that there are some problems that are unsolvable. If a problem is unsolvable, well, then basically what that implies is there's certain things that can't be known. For example, I can't know if a program ever terminates, right? So we talked about TM halt in class, right? Halting machine problem. I can't know if something ever terminates, right? So some things are just fundamentally unknowable, right? That could be another problem that we face. Okay. I suppose I kind of did the examples there for you guys. I guess that's okay. So yeah, so I can have all sorts of kind of ambiguities encoded into my problem. And ultimately what it boils down to is it gives us trouble, because if we have all these problems with our question that we're working with, how do we know that our answer is worth anything, right? How do we know it's well-founded, right? So probably when you guys took a math class at some point, right, maybe in discrete math, they talked about soundedness, they use the word founded, right? Basically the idea is that your problem should be built up from things that make sense, right? They should be, so your problem should be well-founded, right? Meaning you start with stuff that is valid, and also it's sound, meaning that the argument you construct follows from those principles, right? If you don't have stuff to build on, well, then all hope is lost, right? Your answer is going to be terrible anyways, right? You can't just make gold out of, I don't know, bad stuff. I forget the saying. You need to start from a good place, right? So this is something very typical that we see. Maybe even the worst case is what I call a faulty problem, right? So a faulty problem could be a problem that's given to you that is misleading, contradictory, or simply incorrect, right? I mean, maybe it's just impossible. I don't know, right? Typically when you guys go and get a problem from a class, right, you're given a problem that you have, a good chance of solving, right? I mean, I know sometimes people don't think that for my problems, but in general, you're being asked to do stuff, right, you have a good shot at doing, right? So yeah. Okay. I think. Oh, so that was asking about the quiz. So I think Vic raised that earlier, right? I'll end up basically extending it, so you guys can do it anytime because I want to get through some slides. So we'll do that at another point. Okay. So yeah, faulty problem, misleading, contradictory, incorrect, right? You have a bad problem, right? Typically in class, you're set up with something that you can solve. That's not always the case, right? I mean, sometimes, right, your boss is going to come to you with a problem that's like, well, nobody can do it. It's not just that I can't solve it; nobody can solve it, right? But because that answer is worth money, then they still ask you to solve it. So not really a good thing, and not really a good position to be in. All right, so we have some examples over here. And I kind of want to get you guys' input again on these. So I have 4 examples up on the screen. So we'll do our little polling thing here. Let's see. So these could be either fine, ambiguous, or maybe faulty. Okay. So let's take a look at these one by one and see what you guys think. All right. Store a list of contacts. Store a list of contacts such that we can quickly access them by name as well as ID number. How do you guys feel about that problem? Do you feel like you have a good shot at it, or is there something kind of wrong with it? See some marks over on fine, 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 fine. Maybe a little bit of ambiguity there. I don't know what a contact is, but yeah, I think overall I'd say that this number 1 is fine, right? This problem hasn't been posed against me, right? It's not going to hurt me. So I think it's kind of fine, maybe a little bit of ambiguity, but I think I can sort out. Not that bad. All right, question 2. Consider designing a program where you need to store a fixed collection of items. What data structure would you use? What do you guys think? Is that fine? Ambiguous? I wrote fine twice, didn't I? Should be fine over here. Another one should be faulty. Faulty. Anybody want to tell me why example 2 is ambiguous? Which it is. Why did you guys pick that?
Well, it doesn't give you any precise anything. I mean, what structure would you use isn't any precise question. It's an open-ended question.
What you want to know is what structures. Am I just choosing from an array or a list, or is a heap a valid option too? I don't know what structures are there. I don't know what I'm allowed to use. So that one I would be inclined to say that's ambiguous, right? It's not too bad, but it is, the first part is okay, but this gives me trouble, right? That gives me trouble. All right, question 3. Given a set of items, each with a weight and value, determine the number of each item to include in the collection so the total weight is less than or equal to a given limit and the total value is as large as possible. Stolen from Wikipedia there, as we can see. This one is probably a little unfair for me to ask you guys, but if you want, you can take a stab at it. So I see one person put faulty. Anybody else want to take a stab at this? One says it's fine. I mean, it seems pretty well written, right? I mean, I can kind of tell what they're asking for. I know what a solution looks like. All right, so 1 for fine, 1 for faulty. Anybody else want to be a tiebreaker here? Another 1 for faulty. Anybody want to tell me why it's faulty? Because I think it's pretty well written, and that's why I can see people putting fine. Why would it be faulty? So the reason why I might call this one faulty, okay, don't know what the limit is that was coming from David. Okay, anybody else have anything real quick? Why would we say that third one is faulty? And the problem, so I'll tell you guys this, the problem is well defined. It's well defined and it is open-ended, right? So we have flexibility. The problem with number 3 there is actually that's an NP complete problem. So it's a problem which most likely requires an exponential amount of time to solve. So that's maybe my little concern there, right? Is that even though I know what I'm doing, if I'm asked to do it in a reasonable amount of time, it's just not going to happen, right? So if somebody would have to say something like, "Oh, you can run this, right? And I don't care how long it takes, right? Then you can solve it." But there is no efficient algorithm for an NP complete problem, so hey, I can't actually solve the thing, right, in a reasonable amount of time. So that one basically you need to know a little bit more about your efficiency requirement, right? If they say it doesn't matter how long it takes, then yeah, you're fine because you know exactly what you're doing. But if you need it to be solved in reasonable amount of time, I mean, you're sunk. The problem can't be solved any faster than an exponential amount of time. Okay, so yeah. Okay, number 4. Efficiently check if an image is black and white using a neural network. And I think we might get mixed responses on this one. What do you guys think? Is that fine, ambiguous, faulty?
Well, I have a question about that.
Sure, go for it.
By black or white, do we mean only black and only white, or grayscale?
Oh, I meant grayscale, but that's not that would not, but you would need that as kind of additional information there. So let's assume that it's grayscale. That's a good point. People jumped on the ambiguous part. Okay. That's actually that wasn't what I was thinking about when I wrote the prompt there, but yeah. So it is ambiguous, right? Because I don't know, am I looking for black and white or am I looking for grayscale, right? For me reading it, right, I wrote black and white and I thought grayscale because it's like, well, a black and white picture. That implies grayscale, but we really don't want to do the implies thing. We should be specific about what we mean. Okay, so there's definitely some ambiguity there. So yeah, the middle one sounds good. The other thing here, actually, that I would complain about is in this question prompt. Do I really want to use a neural network? I don't know about that, because I could easily. It would be more easy for me maybe to loop over pixels and just see, oh, is it within this threshold? Rather than me having to get a bunch of images, do a bunch of training, figure out how things look. That's kind of a lot more work, and there's going to be a more margin of error, right? There's always some error involved when you use, well, and the machine learning techniques, there's always some error. It might be really small, but there always is some error. Tom, what you got?
Yeah, I said faulty because you can't efficiently use a neural network.
Right. I mean, you could probably, well, the problem is efficiency, right? It's like we need 1 million training samples, and then maybe we get good, but we're always going to have error. And and not only do we always have error, right, but there's a better way to solve it with a higher degree of accuracy. So yeah. All right. So I know we're at time, so we'll go ahead and kind of call it a day there. There are more slides. Probably, I think we'll probably end up having to spend, I think, maybe 3 days on this stuff. So we'll do today. We did today. We'll do Thursday. Probably it'll go into Tuesday as well. Eventually, right, we will get kind of to algorithm stuff. It just takes a little bit of time to get there because we need to, because I want to talk about what it means for problems to be more realistic.
Quick question.
Sure. Yvonne, go for
Why
it.
is number 3 faulty? Because I don't really see anything misleading or contradictory.
Mm-hmm. Well, the problem with it is basically you're being asked to solve a problem that isn't an impossible problem. So even though it's well defined, there's no efficient way to do it.
Why is it impossible?
Because it's the knapsack problem. If you go and search on Wikipedia, there's a page called knapsack problem, and that's where this text comes from. The knapsack problem is basically a combinatorial problem where the only way to solve it is to try a bunch of different combinations and see what's the best one, which one works. And there's no better way to do it. You have to try the combinations, and combinations always looks like an exponential. It's like 2 to the n. It means that your time to analyze this problem will grow exponentially. It'll be infeasibly long for pretty much any realistic input you give it. So you've been asked to solve a problem that's impossible, is what number 3 is. That's why I would consider it to be faulty. Even though it's well defined, nobody knows how to solve it.
Okay.
All right. Anything else, or we'll go ahead and call it a day?
Oh yeah. Also, are you gonna post these? Did you already post the slides? Because
the slides are up. They're in the welcome module. I'll get them in a proper module later on, but I will post them up later on, and you guys will be able to see. It'll be a little bit of a monster slide deck with like 60 slides, but yeah, it'll be up there. All right. Anything else you guys got? I'll go ahead and call it there. All right. So thanks to everyone for coming. I will see you guys on Thursday. Have fun.